Right now, a particle just passed through your body. It had 10 million times more energy than anything humans have ever created, more energy than the entire Large Hadron Collider can produce, moving at 99.999999999% the speed of light. It came from outside our galaxy. It traveled for millions of years, and we have no idea what created it. They're called ultra-high-energy cosmic rays, and according to physics, they shouldn't exist because nothing in the universe should be powerful enough to create them. But this week, scientists finally figured out where their impossible energy comes from. The Oh My God particle, 1991. October 15, 1991. University of Utah's Fly's Eye Cosmic Ray Detector picks up something extraordinary. A single particle hits Earth's atmosphere with 320 quintillion electron volts of energy. To put that in perspective, if this particle was moving any faster, it would have been traveling at the speed of light. It was moving so close to light speed that if it raced a photon across the galaxy, they'd arrive within a fraction of a second of each other. The particle would experience almost no time passing due to relativistic time dilation. A billion-year journey would feel like seconds. Physicist James Cronin said it had as much kinetic energy as a baseball traveling at 60 miles per hour, contained in a single subatomic particle smaller than an atom. Quote, "My God, what could do this?" They named it the Oh My God particle. Since then, we've detected at least 15 similar events. Ultra-high-energy cosmic rays with energies that exceed 100 million trillion electron volts. They arrive at Earth at a rate of just 1 per square kilometer per century. To catch enough of them to study, we needed a detector the size of Rhode Island. Enter the Pierre Auger Observatory in Argentina. 3,000 square kilometers of detection area, 12 years of continuous observation. And the data confirmed something shocking. These particles are coming from outside the Milky Way. The energy problem. What could create them? Here's the problem. To accelerate a particle to these energies requires astrophysical environments so extreme that they border on impossible. Physicist Peter Hillis calculated in 1984 what it would take. You need an object with enormous magnetic fields and an enormous size. The stronger the magnetic field and the larger the region, the more energy you can pump into a particle. Supernova remnants? Too small. Their magnetic fields can accelerate particles to high energies, but not ultra-high energies. Gamma-ray bursts? Possibly. These are the most violent explosions in the universe next to the Big Bang, but even they struggle to explain the highest energy particles. Active galactic nuclei? Supermassive black holes consuming matter at galaxy centers? Strong candidates. Their jets can extend thousands of light years and contain twisted magnetic fields. For decades, scientists believed shocks were the answer. When material collides at supersonic speeds, like in supernova explosions or black hole jets, shock waves form that can bounce particles back and forth, accelerating them to higher and higher energies. But this week, December 2024, new research published in the Astrophysical Journal Letters revealed something that changes everything. The shock theory doesn't match the observations. Ultra-high-energy cosmic rays prefer a completely different mechanism. The breakthrough: magnetic turbulence. Luca Camiso at Columbia University and his team analyzed data from ultra-high-energy cosmic rays and ran simulations comparing two acceleration mechanisms: shock acceleration versus magnetically dominated turbulence. Here's what magnetic turbulence means. In regions near black holes and neutron stars, magnetic fields don't just exist, they're tangled, twisted, chaotic, like a cosmic ball of yarn made of magnetic field lines. When particles enter these tangled regions, they get caught. They spiral around field lines, bouncing between different magnetic structures. Every interaction transfers energy. The particle accelerates again and again, like a cosmic pinball machine, but the ball gets faster every time it hits a bumper. Quote, "It's interesting that these two extremely different environments share something in common. Their magnetic fields are highly tangled, and this tangled nature is crucial for energizing particles," end quote, said Camiso. The simulation results? Magnetic turbulence matches the observed ultra-high-energy cosmic ray distribution far better than shock acceleration. Co-author Glennis Farrer at NYU said, quote, "Remarkably, the data on ultra-high-energy cosmic rays clearly prefers the predictions of magnetic turbulence over those of shock acceleration," end quote. The paper was published December 10, 2024. After 31 years since the Oh My God particle, we finally understand the mechanism. Where they come from, the missing sources. But knowing how doesn't tell us where. The Pierre Auger Observatory detected a dipole anisotropy in cosmic ray arrival directions. They're not distributed evenly across the sky. They come preferentially from a direction about 125 degrees away from the galactic center. This confirms an extragalactic origin. In 2024, University of Wisconsin researcher Angelina Partenheimer investigated whether gamma-ray sources could be the origin. The team modeled cosmic ray propagation from known gamma-ray sources, active galaxies like Markarian 421, blazars, quasars. The result, the brightest gamma-ray sources create a cosmic ray distribution far more uneven than what we observe. One bright source, Markarian 421, dominated the model, creating a dipole 10 times larger than reality. The conclusion? Most ultra-high-energy cosmic ray sources are gamma-ray dim or completely invisible. The team calculated that approximately 80,000 missing sources are needed to match observations. That's 80,000 powerful cosmic accelerators we can't see. They're out there, accelerating particles to impossible energies, and we don't know where they are or what they are. The super PeVatron, Cygnus bubble. But we found one, February 2024. China's Liaoso Observatory discovered a giant ultra-high-energy gamma-ray bubble in the Cygnus star-forming region 5,000 light-years from Earth. The bubble is 10 million times larger than our solar system. Inside it, gamma-ray photons with energies exceeding a peta-electron volt, with the highest reaching 2.5 PeV. This indicates a super cosmic ray accelerator inside the bubble, continuously accelerating particles to energies up to 20 PeV. These high-energy cosmic rays collide with interstellar gas, producing the gamma rays we detect. The source? Cygnus OB2, a massive star cluster containing hundreds of young, hot, massive O-type and B-type stars. Their stellar winds collide with the surrounding interstellar medium and with each other, creating turbulent magnetic fields, the perfect environment for magnetic turbulence acceleration. This is the first supercosmic ray accelerator ever identified. Lead researcher Zhao Zhen said, quote, "This is the first time that the origin of cosmic rays with energy higher than 10 PeV has been discovered," end quote. With increasing observation time, Liaoso is expected to detect more supercosmic ray accelerators. We're beginning to map the invisible network of cosmic particle accelerators across the galaxy. What it means: particles from the void. Think about this. Somewhere out there, in a region near a supermassive black hole, or in a colliding galaxy, or in a magnetar's death throes, magnetic fields twist into chaos. A single proton enters that chaos. It spirals around field lines, gaining energy, faster, faster. For thousands or millions of years, it accelerates. until it reaches 99.9999999% the speed of light, until it contains as much energy as a thrown baseball compressed into a single subatomic particle. Then it escapes, shoots across intergalactic space, travels for 50 million years, passes through galaxy clusters, through cosmic voids, through the Milky Way, and strikes Earth's atmosphere. We built a detector the size of Rhode Island to catch them. We've recorded 15 of the most extreme. We've discovered the mechanism that creates them. We found the first accelerator. But 80,000 more are out there, invisible, accelerating particles to impossible energies. Every second, one of these impossible particles passes through you, carrying energy from the most violent environments in the universe.